Hello everyone and welcome to my channel. Today we will discuss front-end system design related to video calls, and Zoom will be our example. So let's start from our first topic, functional requirements. And the first one is one-to-one and group video calls. This is the core feature of our app, which requires significant effort to design. It allows users to easily switch between one-to-one and group calls, adapting the interface for multiple video feeds. Then recording video will add controls so specific user can start, pause and stop video recordings, with clear indication of the recording status for everyone in the call. Next, share screen. This feature introduces a simple mechanism for participants to toggle between their personal video feed and the content they wish to share with others in the call. After that, raise hand. This introduces an intuitive method for participants to signal their desire to speak or draw attention without interrupting the ongoing discussion. Following this, deep link generation invite people. This functionality enables the creation and distribution of invite links within the app, incorporating essential permissions and security safeguards. Then, view participants. This feature presents a live, updating list of current all participants, complete with indicators of their current status, such as audio muting or video off. And then, user roles. This aspect involves defining real roles within the user interface and controls to fit each role-specific access and capabilities. The next topic is non-functional requirements, and the first requirement is performance. We need to optimize for low latency and smooth video audio playback, ensuring the UI remains responsive even during high load conditions. Then, video quality. We need to adapt video feed quality based on available bandwidth while maintaining as high quality as possible to ensure clear communication. Then, accessibility. The app must be usable by people with disabilities, ensuring broad usability. Now let's take a look at our designed components. The central portion is a canvas layout divided into 4 sections, each representing a video feed from a different participant. These sections are ordered, indicating the active video streams of user 1, 2, 3, and 4. On the right side, there is sidebar listing the participants currently in the meeting. This list is interactive, likely allowing the host or users to manage participants. Above the list, there is an invite button suggesting functionality to add new participants to the session. The bottom of the screen hosts a control bar with action buttons, providing the user with various controls. Raise hand to allow users to express themselves, stop audio, stop video, record, share screen, exit to leave the video conference. Time to add entities and interfaces. Let's add a new title. I divided entities into 4. The first entity is user with user interfaces. User interface defines a user within the system. It has ID, user's full name, and user's role within the application. And it has a num for user roles. It can be admin, participants, guest. Admin can manage meetings and participants. Participants, it's just regular meeting participants. And guest is user with limited access, for example from out of the company. All participants we find in our sidebar component, so the next entity is related to sidebar, where we have interface participants, which extends user. It has is muted, indicates if the participant is muted, and is camera on, indicates if the participant's camera is on. And interface for our invite button with all functionality which we need to invite new participants. The next entity is our reaction. Right now, it's just raise hand, but in real life, you will have a block with different reactions. So interface reaction represents a reaction from a participant. It should have ID of the user expressing the reaction, type of reaction, and time when the reaction was made. Enum reaction time is just enum for types of reaction a user can express. Right now it's just 3, but in real life it can be 2 or 10. And the last main our entity is meeting. Let's add a meeting interface. It has ID, it has title of the meeting, start time of the meeting, end time, which is optional, participants, list of participants in the meeting, is reordered indicates if the meeting is being reordered, and the ID of the user hosting the meeting. And the last interface for actions a user can perform during a video call. Share screen, toggle camera, toggle mute, record meeting. So nothing special, just some function to share the user screen, to toggle the user's camera on off, mute microphone, and start stop recording the meeting. API is our next topic, so let's add a new block here and write API. And here we can use two approaches to make a video call. The first one is WebSocket. WebSockets create a persistent, full duplex communication channel over TCP, allowing data to flow freely in both directions between the client and server. The first one, versatile for various applications, can be used for a wide range of applications beyond video streaming, such as chat and real-time data updates. The next one is good network compatibility. It works well across many network configurations, including those with strict firewall rules. And full protocol control. It provides developers with full control over the communication protocol and data format. From the other hand, it has high latency for media, not optimized for real-time media streaming, which can result in high latency compared to WebRTC. Next one is complex implementation. It requires significant effort to implement efficient video streaming, including handling packet loss and maintaining low latency. And the last one, challenging scalability. Handling large-scale real-time video streaming might require substantial infrastructure and custom development. Next approach which we can use is WebRTC. WebRTC enables peer-to-peer communication directly in web browser using UDP, supporting video, audio, and data channels without the need for external plugins. From advantages, I will add low latency, real-time optimized. It designed specifically for real-time communication, offering low latency video and audio streaming. Peer-to-peer. Direct peer-to-peer connections reduce server load and potentially improve performance. And the last one, encryption and traffic management built in. It supports a range of features out of the box, including encryption, bandwidth management, and NAT traversal. From the other hand, it has some disadvantages, for example, browser compatibility. While widely supported, differences in implementation across browsers can lead to compatibility issues. The next one is complex signaling. It requires a separate signaling mechanism, which can use WebSocket, for example, to establish peer connections. And firewall restrictions. In some network environments, peer-to-peer connections can be blocked, requiring fallbacks. Question for you: what approach should we use? Leave your answer under the video. Before 2019, Zoom used WebSocket approach, but then it started using a Zoom approach, so none of the approaches which we discussed Zoom doesn't use. So the final approach is Zoom approach. Zoom utilizes a mix of patented technologies and web standards, including WebRTC for specific features, to deliver its video. It has a lot of advantages, such as patented optimization. Custom video order and infrastructure optimizations provide a reliable and high-quality experience. Feature rich. It supports a wide range of features including virtual backgrounds, advanced noise suppression, and large meeting capacities. Hybrid model incorporates both patented technologies and WebRTC elements, balancing control with standard web capabilities. WebAssembly enables us to use Zoom's custom video order in web browsers. We utilize the Zoom native client C, C++, code and seamlessly integrate it into Zoom's web client and web SDR. And also, it uses WebRTC data channels for sending data such as participants, raise hand, etc. And it also has some disadvantages. Complex integration. Leveraging Zoom's full feature set within custom web application can be complex and may require dependence on Zoom's infrastructure. Browser support. While Zoom works to ensure broad compatibility, the use of patented technologies may occasionally lead to issues on some browsers or devices. Cost and flexibility. Access to advanced features and Zoom's cloud infrastructure comes at a cost and with certain restrictions, which may not suit all projects or budgets. Zoom approach looks like WebRTC approach, but let's make a list of differences to better understand what Zoom approach is. And the first difference in infrastructure and control. WebRTC decentralized peer-to-peer architecture. Most of the processing and data exchange happens directly between clients, browsers. Zoom centralized infrastructure with patented servers and cloud resources. Zoom controls the routing of video streams, which can offer advantages in terms of quality optimization and scalability. Our second difference is feature set and capabilities. WebRTC standard features supported across all implementations include real-time audio, video, and data channels. Advanced features depend on the application's own implementation. But from the other hand, Zoom offers a broad set of advanced features out of the box, including virtual backgrounds, advanced noise suppression, and large meeting capacities. The next difference in encoding and media processing. WebRTC supports standard codecs and relies on the client's browser for encoding and decoding media streams. Zoom uses patented codecs and processing techniques, potentially offering better compression and quality, especially in low bandwidth situations. The next difference in signaling and session management. WebRTC doesn't specify a signaling protocol, leaving developers to implement their own signaling mechanism, often via WebSockets, to initiate and manage calls. Zoom provides its own signaling and session management as part of its platform, simplifying the process for developers. And last but not least, the difference is the use of WebAssembly. WebRTC itself doesn't inherently use WebAssembly for its core functionalities. Zoom utilizes WebAssembly for several critical operations within its web client. This includes video and audio encoding and decoding, applying patented algorithms for noise suppression, echo cancellation, and possibly for other features like virtual backgrounds. Now, I hope it's more understandable what Zoom approach is. The next topic is high-level design. Let me add a new title for a new topic. Let's imagine we have a video call for 3 users. Every user sends multiple video streams of different qualities for high, medium, and low quality. User 1 sends up to medium quality due to camera. User 2 with a high quality camera sends 3 streams for every quality. And user 3 limited by a poor quality camera sends streams that might only reach low quality. Now the question, what every user will receive back? Let's imagine that they have good connections and laptops, just problems with cameras. Then user 1 receives high quality from user 2 and low quality from user 3. User 2 receives medium quality from user 1 and low quality from user 3. User 3 receives medium velocity from user 1 and high velocity from user 2, representing each user's base stream. So participants receive the maximum velocity each user's MRN sent. But if issues like CPU limitations or poor connections arise, the server determines the velocity to send based on bandwidth, ensuring smooth streaming. So let's add a new block with this information where web server decides which velocity to send based on bandwidth. And let's talk about screen sharing. When screen sharing is active, it's typically treated as a separate stream. So during screen sharing, other participants may receive two streams from the user who is sharing their screen: the shared screen stream and the user's video stream. In summary, while users may send multiple velocity streams, they generally receive only the base velocity stream that their system can handle for each of the other participants, not a combined stream containing all users. But what if we have 2 or 100 participants on the all? Will we have the same logic when every user receives streams from every participant? We have two approaches here. The first one is selective forwarding unit. This is a type of server used in video conferencing applications to manage media streams. It's like a smart router that selectively forwards video and audio streams between participants. It has such advantages: bandwidth, efficiency. It sends only relevant streams to participants, optimizing bandwidth. Velocity adaptation dynamically adjusts stream velocity for each participant's connection. Low latency, because it forwards rather than processes streams, it can offer reduced latency. And scalability, more scalable for larger meetings compared to peer-to-peer setups. But at the same time, line processing requires lines to handle multiple streams, which can be resource intensive. Complexity, more complex to manage compared to MCU, especially in terms of stream synchronization. Server load, while more efficient than peer-to-peer, still increases server load with the number of participants. And another approach which I mentioned is multi-point control unit. It's another type of server used in video conferencing systems to mix multiple media streams into a single stream that is then sent to all participants. It has such advantages: simplicity for lines. Each participant receives one unified stream, simplifying line processing. Uniform experience ensures all participants have the same view and ease of mixing. It can incorporate additional features like layout management and active speaker focus. From the other hand, server resources. It requires significant processing power on the server to mix streams. Limited individual velocity control. It doesn't allow for individual stream velocity adaptation for participants. Potential for high latency. The process of mixing streams can introduce additional latency. Zoom uses hybrid approach here. For regular video calls, Zoom and functional similar to a selective forwarding unit, where each user's stream is sent to the server, and then the server forwards the appropriate streams to other participants. This is efficient for participants' scalability and adaptive velocity management. For certain scenarios, such as when there are too many participants to display individually or for webinar attendees, Zoom may mix the video stream server side before sending a composite video to the users. This reduces the bandwidth and processing requirements on the client side. Now let's talk how users watch a recording video. For recording video, we use chunk-by-chunk saving. As the server receives the data, it processes the streams and typically saves the recording in chunks to reduce memory usage and handle long reorders efficiently. Then the web server processes and then stores the reordered video streams into blob storage. Reordered content from blob storage is distributed through a CDN. When users want to watch a reordering, they access it through the CDN, which delivers the video stream efficiently. Our next topic is UX. We want to write our ideas how to improve user experience. And the first idea is preview flow. Before joining a session, you ensure a preview flow where you let the user test their camera, microphone, and speaker, if supported by the browser. This allows them to accept the browser permissions of accessing their microphone and camera, and even allows them to pre-select which camera and microphone they would like to use in that session. The next idea is join leave notifications. We need to add some sort of notification when a user joins or leaves, so that other users are aware. This is especially important if you are rendering less videos or users in your video layout than users who are present in the session. Then empty state, when user is waiting for people who should join. Permission management. We need to handle system and browser permissions errors. For example, if the end user hasn't granted camera access within the browser or web page, or they have denied access, display the error, enter all action to the end user. The next idea is highlight the active speaker. If you have multiple users in the session, use the active speaker event listener to spotlight them in your UI, or border their video so everyone can visualize who is speaking. The next one is microphone animation. We need to animate the microphone when user speaks. It helps users visualize that their microphone is capturing their voice successfully. And video aspect ratio. Always render the video in a 16:9 ratio, setting the same height and width on the HTML canvas element. Now let's talk about our next topic, which is optimization. The first one is, we need to automatically adjust the quality of the video stream based on users' bandwidth. Then we need to automatically adjust the quality of the video stream based on the user's layout. For example, speaker view, one large video we stream in high quality. If we have view 2 on 2, we need to provide medium-sized video. And if we have a lot of participants, it doesn't make sense to provide a high quality. In this case, we can just provide low quality because the view is very small. It's just an example, we can use another condition how to handle it, but in general, it doesn't make sense to stream in high quality when there are a lot of participants on the screen. The next one is simulcast. We need to send multiple versions of a video stream at different resolutions and bit rates, allowing the server to choose the best stream for each recipient. CDN for distributed delivery. We need to use the content delivery network to cache and deliver video content to reduce latency and be used with recorded video. Virtual list for participants components. For example, if we have 100 participants, it doesn't make sense to render all elements. For bad connection, we can suggest users to disable video, switch off the camera, and preloading the Zoom WebAssembly assets when the user first visits the web page. Now let's talk about very important topic such as accessibility. And the first requirement is keyboard navigation. We need to be sure all features of the video call system are accessible via keyboard. Screen reader support. Make sure all UI components and alerts are properly labeled and can be read by screen readers. Closed caption. Offer real-time caption for users with hearing impairments. The next one is adjustable font size and colors. Allow users to adjust text sizes and color contrast to improve readability. Visual indicators. Use clear visual indicators for muted audio, active speakers, and other statuses. Voice commands. Incorporate voice recognition capabilities to allow users to control the system hands-free. High contrast mode. Implement a high contrast mode for users with visual impairments. Dynamic content announcements. Screen readers should announce dynamic changes in the content, such as a new message in the chat, raised hands, and participants join live events. Ensure that your app provides a good interaction experience for both touchscreen and non-touchscreen devices. That's all for this video. If you have something to ask or to add, feel free to comment this video. See you next time. Bye.